Okay, let's speak about Hall spin qubits. There have been many types of electron spin qubits demonstrated. Here I will just focus on that type of spin qubits which have been demonstrated already for holes in germanium. So in the left side, you see the so-called Loss DiVincenzo qubit, where you encode quantum information in one spin. And on the right side, you see the so-called singlet triplet qubit, where now you have two spins, you have a double quantum dot, and effectively you encode the quantum information in the two spins. Before explaining how the singlet triplet qubit works, which is the subject of my presentation, let me remind you the addition of two spin 1/2 particles. So you can have either spin up or spin down. Since we are working with holes, we should always think of a pseudo spin up or pseudo spin down. So if we combine them, we can get the T plus state, the singlet state, the triplet zero state, and the T minus. Due to the wave function overlap, or else stated due to the exchange interaction, the singlet has an energy difference to the three triplet states. And when there is no magnetic field, the three triplet states are equal in energy. One more concept which we need to refresh in order to understand how a singlet triplet qubit operates is Pauli spin blockade. So let's imagine, again, we have our double quantum dot, and now we think of how we can put the two spins. So we can have one hole in the left dot, one hole in the right dot with opposite spins, and then we speak about the singlet 1-1 state. We can have also the triplet 1-1 state, where now we have again one hole on the left dot, one hole on the right dot, but now the pseudo spin points in the same direction. Of course, we can have also the case that now you have both carriers, both holes, located in the same quantum dot, and now we can have the singlet 2-0. So two holes in the left dot with opposite spin. And in principle, one would think that we can have also the situation in which now we have both carriers in the left dot, but with the spin pointing in the same direction. However, that is not possible because the triplet state, the triplet 2-0 state, is too high in energy and typically non-accessible in our experiment. So let's move on to understand how to operate a singlet triplet Hall spin qubit. How does the energy diagram of a double quantum dot look like? So again, I show you below the energy diagram the two configurations. So you can have either two charges on the left dot, or you can have one charge on the left dot and one charge on the right dot. And whether the one configuration or the other is favorable depends on the detuning, which we denote epsilon. So it depends effectively how we tilt our potentials defining the double quantum. If now you plot the energy versus this detuning parameter, in red I plot the energy of the 2-0 state, and in black I plot the energy of the 1-1 state. What happens now if I will turn on the tunnel coupling? But before doing that, let me remind you that I don't consider in the 2-0 configuration, as I explained already before, the triplet 2-0 is very high up in energy, so we will forget about it. Let's turn on tunnel coupling. If we turn on tunnel coupling between the two double dots, what happens? Practically, we have hybridization taking place. So practically, we get a ground state hybridized singlet and an excited state singlet. And the triplet, due to Pauli spin blockade, does not hybridize, so we still have the T1-1 state. If now we switch on also the magnetic field, now the three triplet states split in energy, and if effectively we want to see this diagram in the perspective that we want to work in the picture where we think that our triplet energy is constant, is zero, and that the singlet energy is changing. That's the energy diagram we have in mind, and that's how it looks like if we take into account more details, which I'm going to elucidate in the next slides. Singlet triplet qubits have been investigated since a long time. Actually, the first spin qubit ever operated was a singlet triplet qubit by Jason Petta back in 2005. It was in gallium arsenide. So there are two families of singlet triplet qubits. The one family operates based on the fact that you might have a difference in the magnetic field in the two dots, or you can have a difference in the G factors in the two dots. And about such a singlet triplet qubit I'm going to speak about, and if you want to read more details, please take a look at the paper of Daniel Giro. Singlet triplet qubit, how does it work? If you write down the Hamiltonian of our qubit in the singlet T0 basis, it is a 2 times 2 matrix, and the interesting point is now to compare the exchange interaction J with the term delta G mu BB. So if we are at large detunings here, exchange interaction becomes very small. Ideally, it drops to 0. So then our Hamiltonian takes this form. So it's not diagonal anymore. So which means that the singlet and the T0 are not anymore eigenstates, but the up-down and down-up are eigenstates. On the other hand, for small detuning, so if we are, for example, in the position where we have the orange arrow, now our exchange interaction J is much, much bigger than delta G mu BB. So we can think of the Hamiltonian written in that form. So now it's diagonal, and the singlet and T0 are eigenstates. So let's see how we are going to make use of the fact that practically we can change the Hamiltonian by simply moving in detuning in our double quantum dots. Okay, let's start. What we do, we always initialize in a singlet 2-0. And what we are now going to do is we are going to apply a very fast pulse in detuning in order to go over the anti-crossing. And then we are going to wait at this point. So we act with a, and so we want to see how is our state evolving in time when we act on it with a Hamiltonian. So as stated, we started with the singlet state, we pulse very fast to this position, and now we wait. Now we express the singlet as up, down, down, up, because remember, at this point, the singlet T0 are not eigenstates. However, the up, down, down, up are eigenstates, so when the operator acts on up, down, effectively, we can get the energy of the up, down, down, up state. If you do the math, what you will get is that if you wait, the evolution of your state leads to the equation that it gives you cosinus A singlet minus I sinus A triplet, where I have defined as A delta G mu BB times the time divided by 2h bar. And if now you choose A to be pi over 4, you will end up with a state which is 1 over square root of 2 singlet minus I square root of 2 triplet. So effectively what we see is that by pulsing from the singlet to 0 deep in detuning and waiting the proper amount of time, we have not done anything else than an X rotation. So we can think then that our G factor difference is the axis around which we can do X rotation. What is now going to happen if we switch from that position? So here is where we do our X rotations, and now we pulse back in order to switch on J. Again, we want to see how our state is going to evolve in time. So Now our Hamiltonian has changed. So now we have again the diagonal Hamiltonian, which has the singlet and the T naught as eigenstate. So if you now act with that operator in our new state, which we found in the previous slide, and you do the math, you will find that for the correct time, and by correct time I mean when the exchange interaction multiplied by the time divided by h bar is equal to pi, you will end up in the state minus 1 over square root of 2 singlet plus I triplet. So effectively, what we see is that we have done now a Z rotation. So the exchange interaction allows us to do Z rotation. Reality is a bit more complex because neither we can switch completely J off, nor our exchange interaction is so much bigger than our delta G mu BB, which means that in reality, when we do rotations, we have both J on and the G factor difference is not zero. So practically, when we do rotations, we do rotations along an axis which is defined by the angle theta. So let's get the singlet triplet oscillations. Again, as a refresher, what we are doing, we start in the singlet triplet, we pulse very fast, then we wait, and then we get coherent rotations, as we have seen, and then we are going to pulse back, and depending on whether we end up in a singlet state or a triplet state, we can go back to a 2-0 occupation or not. On the right plot, you see this measurement where we measure effectively the reflectometry signal, where high signal corresponds to a higher triplet probability versus the time we are spending at this position and the magnetic field, and you can see the so-called X rotations. And if now you plot the frequency versus the magnetic field, you can see that actually already a bit above 4 millitesla, you can reach X rotation frequencies exceeding 100 megahertz, and we have a delta G factor, a G factor difference of 2. These were the X rotations. Let's see how we are going to do exchange oscillations. So for doing now exchange oscillations, practically what we are going to do is we are going to do a slightly more complex sequence. We start from singlet 2-0. We will pulse deep in the tuning. Then we will allow coherent oscillations for time equal to pi half. Then we will pulse to switch on J. We will do a Z rotation, and then we will apply a second. Then we will go back deep in the tuning. We will apply a second pi half pulse, and then we will read out. And if you do that, and again you measure the reflectometry versus the waiting time and the detuning, you can see exchange oscillations, and you can see that the coherence time depends on the detuning, and that is known that for high exchange interaction, coherence is more limited because charge noise is enhanced. And with that, I have finished my presentation about germanium qubits, multispin encodings.